All right, welcome to part 4 of our lecture series from Monday, March 6th, where we talk about kind of a facet of valence bond theory, which is this concept of hybridization and hybrid atomic orbitals. So I know that sounds kind of weird. We've already discussed like resonance hybrid, so you might get an idea of what a hybrid means in general, but let's dive into this. So I've started here by making a statement which says that in covalent compounds, we have to remind ourselves that the kinds of bonding orbitals, aka our valence orbitals that we're looking at, are between nonmetals, which always have these valence orbitals ns and np. So regardless of what kind of nonmetal I'm looking at, according to Aufbau, if I were to draw like my energy or orbital box diagram, I would always have my s orbitals slightly lower in energy compared to my p orbitals, which again, there are 3 of them. So if I know that these are the valence orbitals, but they aren't quite at the exact same energy level, then how is it that I can look at overlaps of these valence orbitals with other valence orbitals on other atoms, right? I have to have some kind of interference or overlap with other orbitals such that the orbitals on an atom that's going to be involved in some kind of bonding are equalized, meaning we're going to try to fix or adjust or account for this energy disparity that exists between our valence s and our valence p orbital. The way in which we do that, meaning the way that we can create orbitals on our atom that is going to be bonded to something else that are equalized, is we form hybridized atomic orbitals, aka our atom will combine its valence s and p orbitals in some manner, thus creating a new hybrid atomic orbital. So let's look at what on earth is happening here. So for example, let's look at H2O. So we're going to kind of do Lewis side by side with valence bond theory. So if I were to draw my Lewis structure for H2O, I would ultimately arrive at something like this. And then if I were to think about valence bond theory, that's when I have to go back into the world of orbitals. So if I think about the oxygen valence orbitals, how would I pull up in a periodic table? This would be my helium core electrons, followed by my 2s2 and 2p4 valence orbitals. And then my hydrogens, these are each my 1s1. And because I have this 2s and 2p, which if I look at the oxygen orbital diagram, 2s, and I'm just going to draw this vertical to save space, 2p, it would look something like this. So 2s, 1, 2, 2p, 1, 2, 3, 4. Okay. Remember, valence bond theory says that I am looking to combine half-filled atomic orbitals such that when those orbitals overlap, they create a spin pair. So I'm going to draw my other hydrogen atom here. So it looks to you probably right off the bat that if I were to combine or overlap these orbitals and these orbitals, then I might be able to form a bond in the region of overlap between those orbitals. But then how is it that I can involve all of my valence orbitals and oxygen in that bonding scheme? And the answer comes through with hybridization. So let's go ahead and combine our s and p valence orbitals. And in this particular molecule, let's just see what happens if we combine all of them. Like, let's create a bunch of new hybridized orbitals. So if I were to take my 2s and add it with my 2px, 2py, 2pz, that is 1 orbital, 2 orbital, 3 orbital, 4 orbitals. I'm going to make 4 new hybridized orbitals. And again, the whole point of these hybridized orbitals is to bring these orbitals, the ns and the np, to some equalized energy state. So if I were to draw this, I would find something like this. I'm creating 4 new orbitals. And since they came from me taking an s and adding it together with 1, 2, 3 p orbitals, let's call this an sp3 hybrid. So if I were to then fill in this sp3 hybrid with all the electrons that were contained in my 2s and 2p separately, so this is 2s2, 2p4, which is 6 valence electrons. So I'm going to fill 1, 2, 3, 4, 5, 6. And now I see the opportunity here to have a bond formed by these half-filled orbital overlaps with the hydrogen and oxygen from the sp3 hybrid orbital. And also here I see this opportunity as well, so I can form a bond to my other hydrogen atom. So what on earth does this look like? So anytime I'm combining an S and a P, I guess something that looks like this. So this is kind of a combination of my S and my P. And when I say combination, I'm talking about like a linear combination, meaning I can look at their destructive and constructive interference. So this is what our hybridized orbital looks like. It's just in this case, we have 1, 2, 3, 4 sp3 hybrids. So if I wanted to kind of follow this little shape convention here, I would have my oxygen atom, and around that, I would have 1, 2, 3, 4. 1, 2, 3, 4 of my hybridized orbitals. Like so. So this is our oxygen atom. This has 4 sp3 hybrid orbitals instead of having instead of having 1 2s orbital and 3 2p orbitals. And these are what are going to be able to come together and form our bonds with our hydrogen. So let's fill in our electrons. So 1, 2, 3, 4, 5, 6. So this is my oxygen atom. And then if I were to look at my hydrogen atoms, these of course are just my 1s. Each with 1 electron. And if we see these atomic orbitals here that are half full, these are the ones that have the potential to overlap and create a spin pair. So I might see something like this. So bear with me as I sketch this out here. So in here in yellow is the minor lobe, or result of my combination of p and s orbitals coming together. And then I've got my hydrogen atoms with their s orbitals. Probably should have drawn this bigger. Let's do that bigger. Okay, here are my major lobes as a result of my S and P coming together. And here are the minor lobes. Okay, we had oxygen, 1, 2, 3. Oh, let's see here. Let's wait to add in these oxygens. So let's go ahead and draw now our orbital overlap with our hydrogen atoms. Trying to give myself as much overlap space as possible. Okay. So here is oxygen. Here's my hydrogen. It is these electrons that are going to be spin paired according to valence bond theory in the overlap. And if I compare this to Lewis, which says that I have oxygen singly bound to hydrogens with 2 lone pairs, we notice that this agrees. It's just that the covalent bond to oxygen in the Lewis model is now defined by this overlap region as a result of our hybrid atomic orbitals on oxygen overlapping with the 1s electrons on 1s orbital on hydrogen, creating spin pair in that overlap region, leaving behind one, two, three, four, or 2 lone pairs, each of these found in our non-bonding orbitals here. Now we have a name for this pink overlap region. So overlap of some kind of hybrid orbital and atomic orbital, or just in general, any kind of atomic orbitals that is quote unquote head on. So just like here, right, we saw that we were going to just straight on collide or overlap this 1s orbital from hydrogen and then this hybridized orbital from oxygen. That's a head-on collision, head-on addition. So the overlap, which is this pink region, from this head-on combination forms what we call a sigma, same symbol we've seen for standard deviation, bond. So if I were to look at my water again, this overlap region here that contains my spin pair electrons, these are my sigma bonds. Okay. This is an introduction to valence bond theory and the idea of hybridization that can occur in valence bond theory. We have thus far talked about like the sp3 hybridization. That's what we've seen so far. So go back to our lecture plan. We've seen sp3 through water. We haven't really talked about why it is that I knew it was going to be sp3 and not something else. So what we're going to do instead is on Wednesday, we're going to go into more detail about the how and the why we create these atomic orbital hybrids. But in general, what you need to know for now about hybrid orbitals on an atom is that when we look at these covalent compounds that are bonds between nonmetals, we are looking at some orbital interactions that exist between their valence s and valence p. And if we want to have those valence s and valence p interact with other atoms' valence orbitals, then those valence s and valence p need to combine with one another in some way that allows them to arrive or be at the exact same energy level. So we're trying to fix this issue that we saw from Aufbau with the NS and the NP not being at the same energy level. And hybridization is kind of our fix to that solution. So we'll pick up with valence bond theory on Wednesday. Tomorrow in lab, you will see our discussion of VSEPR theory, which is related to valence bond theory, but we can kind of talk about it without all the nuance of valence bond theory. And then ideally by the end of day on Friday or next Monday, we will wrap up with our final bonding model which is something called molecular orbital theory. Thanks, folks.